Hi everyone, I'm Raghavendra Pothukuchi from Yale University, and I'll be presenting Distill, domain-specific compilation for cognitive models. This is joint work with Vesely, Ketaki, Joshi, and Professor Abhishek Bhattacharjee from Yale University, Samyak Gupta, and Professor Jonathan Cohen from Princeton University. Cognitive models are computational models that simulate processes underlying cognition. A cognitive model takes in inputs such as stimuli and describes how neural and mental mechanisms act on these inputs to produce outputs such as decisions. These models are used to study the behavior of cognitive phenomena over time. For example, how decision-making evolves over time and when decisions are arrived at. The models are also used to collect distributions of outcomes when they contain stochastic elements, which happens frequently. To obtain these types of information, the models are run several thousands of times. Insights from cognitive models have been influential not only in the brain and behavioral sciences, but also influenced the fields of machine learning and artificial intelligence right from their inception. Unfortunately, cognitive models are running very slowly today. The models and frameworks are developed in high-level languages, contributing to slow execution. Consider the Simulink modeling framework, for example. This framework is written entirely in Python. The models that it processes are also written in Python. Cognitive scientists prefer Python because it enables them to prototype their designs fast and provides them with access to optimized scientific computing libraries. Unfortunately, the execution time is too long. Things can get even worse when we consider the fact that to simulate human-like cognition, the models are incorporating many components from various frameworks. The slowdowns have reached such a state that certain models take several days to weeks to complete, severely impeding scientific progress. It is important that we develop solutions to accelerate cognitive models. Among potential solutions, one approach is to develop a new domain-specific language. Unfortunately, the field of cognitive science is too broad of an environment, and the various subfields have their own styles and degrees of detail to which they model cognition. It is difficult to obtain a canonical set of language constructs that works across these different environments. Furthermore, there are logistical challenges in that a new language requires community adoption and large-scale porting efforts of existing models and frameworks. Another solution is dynamic compilation. This is a great drop-in replacement, but unfortunately, existing tools like PyPy and Piston are designed for general purpose use and do not exploit the opportunities present in cognitive models. Moreover, the tools are effective when the models are heterogeneous. That is, they contain components from many frameworks. Our proposal to solve this problem is Distill, which is a domain-specific dynamic compilation tool for cognitive models integrated with Simulink. The key insight is that expensive dynamic language features simplify programming, but aren't used for execution. Therefore, Distill aggressively eliminates these features and lowers entire models into LLVMIR. We also discover that we can use compiler data flow analysis to automate several model-level analyses and incorporate this feature in Distill. Thus, Distill can automatically find the best parameters in a search space, compute the sensitivity of outputs to inputs, and more. Distill does not require any source code change for models and also has support for offloading computation to accelerators like GPUs. In the design of Distill, we minimize software engineering efforts by maximizing reuse of existing LLVM infrastructure. Next, I will introduce Distill using an example cognitive model. This cognitive model is about what is known as the predator-prey task. In this task, there is a screen with three entities. The first is a player whose position on screen is controlled by a non-human primate, like a monkey using a joystick. The second is a predator that tries to capture the player. And the third is a prey which the player must capture. The goal of this task is for the monkey to steer the player and capture the prey while avoiding the predator. Now, the accuracy with which the monkey perceives the location of these three entities depends on the attention that it allocates to each of them. Once it observes their locations, it takes an action to steer the player. This task is modeled in an environment like Simulink in the following manner. There are three inputs to the model, which are the exact locations of the three entities. The role of attention in shaping perception is modeled by the control node, which takes the three exact locations and produces the locations that would have been observed by the monkey. There is an action node that takes these observed locations and produces a direction of movement. The action node could be a user-defined function or a standard library function from Sinulink. The control node searches for the best attention allocation by minimizing a cost function. The cost function has two components. One is the cost of allocating attention, and the other is the quality of the move that arises out of a given attention allocation. This value is computed by an objective node. It can be seen here that the control node has to search through a multidimensional attention space to identify the best attention allocation and the best direction of movement. Now, when this model is run in an environment like Sinulink, let us see what happens. On running the model in Sinulink, the framework first sanitizes the model. This step checks that the nodes in the model are properly connected and that they are initialized to default values. Sinulink also requires that the data types and shapes of all inputs and outputs must stay the same even in the actual model execution. Now, this information greatly benefits dynamic compilation. Next, the framework parses the various inputs with which the model is to be run. In the predator-prey example, the inputs are the locations of the three entities. So the various inputs are the locations of the three entities at various points in time. Next, the framework runs the model with each of these inputs. The execution of a model with one input is known as a trial, and the number of trials is specified by the user. In the execution of a trial, the framework first checks for termination conditions. In the predator-prey example, this could be the identification of an optimal attention allocation and an optimal direction of movement. As long as these termination conditions aren't met, the framework finds all the nodes that are ready to run in each iteration and runs them. There are a couple of points that are noteworthy here. The first is that the execute method in the various nodes lie on the hot path, and we have this information readily available from the framework without expensive profiling or tracing analysis. Second, we know that the execution switches between the scheduler and the nodes. This is a source of overhead. This also means that even if we independently optimize and compile the nodes, if we do not compile the framework, the transition between the interpreted mode and the compiled mode would prevent us from seeing significant performance improvements in the model-wide execution. Existing dynamic compilation tools cannot capitalize on this knowledge. Once the trial execution is complete, the framework collects the results from the output ports of all the nodes marked as outputs and returns the result. Once all the trials complete, the framework concatenates these results and returns them to the user. With this domain-specific information, let us look at the different stages of Distill. The first stage of Distill is dynamic to static data structure conversion. Recall that the type and shape information of all the values in the model is available from the sanitization pass. Distill uses that knowledge to create structs for holding the values in the scheduling iterations, the read, write, and read-only node parameters. It creates arrays for storing the overall inputs and outputs. It also converts the data structure that tracks the scheduling status of the various nodes into a Boolean array. It converts lists and dictionaries to structs and string keys to enumerated data types. The second step is code generation. In this step, Distill uses templates for nodes and standard library functions that are filled with computations in the model. Distill generates monomorphic code by specializing functions to the types of the arguments with which they are called. Distill also lowers codes from all the nodes and the scheduler into LLVM. This means that the computational functions become LLVM instructions and intrinsics without any external library calls. Finally, Distill generates modular IR for each function. This not only helps in verification, but also enables the user the same IR for serial and parallel execution later. Next, Distill runs standard LLVM optimizations on the code, which are now more effective because they can span longer regions of the code. Distill also supports parallel execution and offloading computations to GPUs. Opportunities for parallel execution exists in the control nodes that have to perform a search. In this case, Distill creates parallel threads in Python, each running a segment of the control node search. We use the same IR for the serial and parallel execution. We use per-thread pseudorandom number generators for debuggability. Finally, to target GPUs, Distill uses the NVPTX backend with LLVM to generate kernels for the evaluation of each point in the search space. These kernels are imported using PyCUDA. Finally, Distill has support for model analysis using compiler analysis. We discover that several types of model analysis that cognitive scientists undertake, such as identifying the sensitivity of outputs to inputs, can be entirely done by compiler data flow analysis. When a cognitive model is run in this mode, Distill aggressively inlines and optimizes the LLVM code beyond what standard optimizations do. And then it uses compiler analyses like value range propagation and scalar evolution that are extended to floating point operations. Here is an example of how model analysis benefits cognitive scientists. Consider the case of finding the optima in a parameter search space. This could be, for example, finding the optimal attention allocation in the predator-prey task. In the conventional approach, the model has to be evaluated at all points in the search space to find the optimal parameters. In contrast, Distill combines value range propagation with binary search to find the best parameters. Consider, for example, a simpler version of the predator-prey task where we have to find the best attention allocation only for the prey, ignoring the player and the predator. In this case, the chart on the slide shows the level of attention allocated to the prey on the x-axis, and on the y-axis, we have the overall cost function that has to be minimized. The conventional approach requires evaluating the model at each of the levels of attention and from which we can find the minimum. In contrast, Distill estimates the range of the cost function from the levels of attention and performs a binary search. It identifies that the region on the right contains the minimum and progressively refines it to identify the overall minimum in about 7 rounds of binary search. This does not require evaluating the model at all, saving significant resources. The paper has more instances of how model analysis can benefit cognitive scientists. Next, let us look at the performance evaluation of Distill. We evaluate multiple cognitive models that are developed in the Sinulink framework. For certain models, like the predator-prey model, we evaluate various sizes of the model. Notably, the multitasking model uses PyTorch in addition to Sinulink. That is, it uses code from 2 different frameworks. We evaluate 4 environments with and without Distill. The first is CPython, which is the default Python implementation. The second is PyPy, which is an alternative implementation with just-in-time compilation. We also evaluate PyPy without JIT compilation. The fourth environment is Piston, which is another alternative implementation that has JIT compilation. Piston, like Distill, also uses LLVM-IR. The overall performance results are shown in this chart. The x-axis has the different cognitive models that we evaluate, including the overall average. And on the y-axis, we have the execution time normalized to that of the standard CPython execution. The first 4 bars for each model have the execution times for the environments without Distill, and the remaining 4 with the pattern show the execution times with Distill. Consider the average results first. On average, the PyPy environments have about 70% slower execution than the standard execution. This is surprising because these tools are intended to provide performance benefits, whereas we see slowdown. On the other hand, Piston provides an execution that is about 1.5 times faster than the standard execution. On the other hand, when Distill is used, the execution becomes about 27 times faster. Next, consider the multitasking model. This model cannot be run in PyPy and Piston because they do not support running PyTorch. In the standard CPython environment, using Distill makes the execution 896 times faster by eliminating the transitions between the various frameworks. Next, consider the Botvinnik-Stroop model. This model does not run in the PyPy environments because it runs into an out-of-memory error after exhausting all the 16 GB of memory present on our test machine. On the other hand, with Distill, the framework is able to achieve around 923 times faster execution. Distill is able to provide significant speedups from its domain-specific compilation by aggressively eliminating dynamic data structures and by lowering entire models and frameworks into a common LLVM-IR. Next, we consider the performance of parallel execution. Here, we take the predator-prey Excel model and consider 2 new environments that target a multi-core CPU and a GPU respectively. The chart on the slide shows the execution times of these 2 new environments normalized to that of the optimized serial version. With a multi-core CPU, execution is 4.9 times faster, and with a GPU, execution is about 6.4 times faster. Note that the parallel and GPU execution use the same IR requiring no source code change. The performance on GPU still has room for improvement because the models are memory bound, and we are currently investigating techniques to improve GPU performance. Finally, we highlight the importance of end-to-end compilation. Here, we take the Botvinnik-Stroop model and consider an environment where only the model is compiled but the framework is interpreted. The chart shows the execution time of this environment normalized to that of the standard CPython environment. With node-only compilation, we see an execution that is only 3.4 times faster. The reason is that even if the model is compiled, the transition between compiled and interpreted modes limits the maximum performance speedup that we can see. On the other hand, compiling the entire model and the framework results in a speedup of 774 times over standard CPython execution. This highlights the importance of compiling the entire model and the framework together. To conclude, cognitive models are important, but cognitive model execution is slow and needs acceleration. Unfortunately, existing dynamic compilation tools aren't fully effective. We propose Distill, which is a domain-specific compiler for cognitive models. Distill does not require any source code change, supports parallel execution, and reuses LLVM infrastructure. Distill also uses compiler analysis for fast model analysis and optimization. Our full paper has details about Distill's analysis capabilities, the models we test, additional results, and future work, including the integration of Poly with Distill. The Simulink framework integrated with Distill is publicly available and is already being used in leading universities and classrooms worldwide. Thank you.